Thank you, and welcome to Job Scheduling with Slurm, the fourth in the AceNet Basic Series for 2026. Um, let's see. Uh, so I'm not going to assume that all of you have necessarily been to the other three basics earlier this week, but I'll assume you at least know the general outlines of what's going on there. And you will also know the general outlines of what AceNet is and what we do. You've heard this already. I won't review it again today. Um, what's going to be a little more important today is that AceNet is a regional partner of the Digital Research Alliance of Canada, which we may just call the Alliance, or maybe we'll just call DRAC. The naming varies depending on who you're talking to. Um, and the general theme today of how you schedule jobs happens mostly on high performance computing clusters that are shared with AceNet as part of this national network, the Digital Research Alliance. I want to remind you of what you probably saw if you were in Tuesday's lesson, and just want to reemphasize something that you've probably already seen, which is to reinforce your mental model of what a high-performance computing cluster is and how it works. The fundamental thing that an HPC cluster is a whole lot of computers. So we got a stack here of the creatively named 1, 2, 3, 4 through 100. I think the national clusters these days have a number of computers measured in thousands, over 1,000 in any case. They're, of course, all networked together, and there may be one or two or three special ones that we call login nodes or head nodes. There's going to be a bunch of other computers in that same machine room with them that are the storage array, and on Alliance computers, that storage is going to be divided into home, project, and scratch, as you should have seen earlier this week. The login nodes are the only ones that are directly connected to the internet. The other compute nodes may or may not have free access to the internet. It depends on the policies at the individual HPC site. And so your mode of operation on this is to log into a cluster. You upload your data and possibly your code via the login node. Sometimes there's also a data transfer node. Don't need to worry about that today. And that data and code will go on to the shared storage over here, home or project or scratch as appropriate. And then you test your code or whatever calculation you're going to be doing on some test data on a login node, just to make sure that it works as expected, and you have an idea, what the paths are to the files and all that kind of stuff. Just a small test, make sure everything's working. And then you are going to submit a job to the scheduler. This is a typical mode of operation. We'll talk about some other things like interactive use later on today. Typical mode of operation, once you've tested things, then you are going to submit a job to the scheduler, and you can submit multiple jobs. This is one of the features of a batch job system like we're talking about in today's workshop. You can submit a bunch of jobs. They go to a piece of software that we generically call a scheduler. The specific one we're using here is called Slurm, but we'll come back to that. The scheduler software, its job is to figure out which of these 1,000 or more computers has some free CPUs and some memory on which you can run your calculation. It keeps track of these things. It will then dispatch your job to some appropriate machine that meets your requests and that has the right resources available. And then when the job is finished, it may send a notification back to you if you have asked for one, or it may just leave the data where you've told it to leave the data, and you can come back and find that later. So I mentioned that the particular schedule we're using is something called Slurm. It's It's a product. It's actually a commercial product. It's now I think owned by NVIDIA, but that's a relatively new development. It doesn't really matter. Um, the point of Slurm or the scheduler is that we've got hundreds of users on these clusters, all trying to run multiple jobs. We need some sort of sense of order to keep things organized. One of the things Slurm does, the main thing Slurm does, I just described, which is scheduling, decide which job begins next and on what nodes. It's sort of like the traffic cop for the cluster. Tells the jobs rather, it doesn't tell you what to do. You tell it what to do and it does it for you. It figures out where to send what work. Oh yeah, Slurm, by the way, originally stood for Simple Linux Utility for Resource Management. I'm not sure the simple applies anymore, so we don't usually expand the abbreviation. Let me see. So, what does it actually look like in practice? It looks like this. Typically, you create a job script, which a job script is simply a shell script. And if you were in yesterday's session, you're now fairly fresh on what a shell script is. A job script is simply a shell script that you're going to give to the scheduler, which then becomes a batch job. So you create a job script, a little thing saying what you want to do, and then you submit it. So inside the box here, we have 3 lines. The first line, we pronounce that #bang/bin/bash. That's just telling the scheduler what shell dialect to use. It never changes. Basically, you just copy that one line from one job script to the next, and you never mess with it. If you know the term boilerplate, that applies here. #bang bin bash is boilerplate. And then we have a line that says #sbatch --time equals, well, it's got the word time in there. So if you're guessing that's a time limit, you're absolutely correct. And you can probably interpret the format for the time limit. That's days, hours, minutes, and seconds. We'll come back to that as well. And then you just say, here's the name of my program, and I want you to take the input from some input file. Like any other program running on Linux, if you don't tell it where to send the output, it will send the output to a generic location called standard out. And I'll come back in a few minutes to where that goes in the case of a batch job as well. And then once you've got this box here is your job script, once you've got that made up, you submit it. The command to do that with Slurm is called sbatch. Sbatch, name of the file. And Slurm should respond, if everything goes right, with something like submitted batch job, some random looking number. That's actually a sequence number. We call it the job ID number, and it's unique on any given cluster. So each time you type sbatch to submit a job, you will get a new job ID number, even if it's the same script over and over again. Okay, so this is basically a recap. Sbatch command submits jobs to the scheduler. You can supply options to sbatch. It'll take options like how much time to give the job. We've got a time limit inside the job script here in this previous slide. That says 0 hours, 1 minute. Here in the next slide, we've got a time limit supplied on the command line. That says 30 minutes, 0 hours, 30 minutes, 0 seconds. The command line will override what's inside the script. So this is inside the script, you'll typically put what you'll usually want. And if you're messing around trying to test things, then you may want to vary the time limit or other options that we will see as we proceed into this talk. So sbatch, name of the file, you can add some options that follows the usual Linux rules for options. There are single dash, single letter abbreviations, and there are double dash full name options or arguments that are much easier to remember. I'm going to generally use the double dash ones. So besides sbatch to submit a job, you will want to be able to check and see what the state of your jobs is. Has my calculation started? Has it finished? Is it working? Is something gone wrong? The first and most frequently used command for that is sq. Now, in the formal Slurm documentation that I'll show you later, the full name of this command is squeue. That is to say S for Slurm in front of the English word for a lineup, a queue. But at AceNet and on Alliance clusters, we have an abbreviated form of that, just the letters SQ, which tells you about the state of your jobs. If you type the whole squeue command, you'll get information about everybody's jobs, which you probably don't need to see. So if you just use the short form, you'll get the short output, much more useful. SQ will tell you, it'll tell you what jobs you have in the system listed by their job ID here. And it'll tell you the most important thing you want to know, which is the job running yet or is it not? R stands in the ST column for state. R stands for running, PD stands for pending. If you type SQ like down here below and you just get the headers, job ID, blah, 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 and no actual numbers and no actual names, etc., then that means that all your jobs have finished. Hopefully they finished well. We'll look into that in a moment. Let's see. What else is there? All right. SQ will show you a bunch of other information as well, which you can pick out some of here. I pointed to the job IDs already. The time left is probably the one that's most interesting to you. For a pending job, that's just going to show you how much time you requested, which is nothing new and surprising. For a running job, it shows you basically a countdown. So job 1531853 here has got another 15 minutes and 47 seconds left before the time limit that we gave it runs out. Oh, and it'll also tell you which node in the cluster it's running on. If you're interested in that, that's not always useful information, but sometimes it is. And you can see some things about how many resources it's requesting. We'll talk more about those as we go too. The job IDs get a red circle because job IDs are quite important. I'll talk about runtime limits in just another slide or two. So good question there in the chat. We'll come to that in a second. Slide or 3 or 4. I can't remember how many slides, but I'll come to it, I promise. So let's just review where we are so far. You make up a job script. You say, I want to run this program. Take the input from here. Slurm, you run sbatch. Slurm gives you back a job ID number. You can check on it using SQ. Where's the output going to go? I mentioned standard output earlier. In the case of a Slurm job, a Slurm batch job, the standard output is generally sent to a file with a name like this, slurm-job ID number .out. You can pick a different name for this file if you like, and you can find out how to do that in our documentation. But if you just leave it at the default with the job ID there, then that has the advantage that we can always sort of find our way back to the ID of the particular job. And if we're troubleshooting and something went wrong, almost the first thing we're going to ask is, can you give me a job ID? And so if the job ID is right there in file name, brilliant, easy to do. And so, yeah, so if you've got an application that normally prints information to the screen, then it'll go into this slurm-blah, blah, blah, .out file. You can also choose to redirect your output inside your job script as well. So you're running the application like you learned a day or two ago with / name of a program. Then a single angle bracket, single greater than sign will overwrite the file myoutput.out here. 2 of these will append it to that file. You can also use a fanciness involving a pipe and T to both get it standard output and to a file if you like. Finally, what do you do if something goes wrong? Well, don't panic. We've got everything pretty nicely siloed, so you're not going to be doing. It's really quite difficult to do any damage to the rest of the system. But you may decide, okay, this job is actually not doing any good. It's just sitting there spinning its wheels. I want to stop it. What do? The command you want is scancel. S again for Slurm, cancel, kind of obvious. And you give a job ID. So there's first important use for that job, those job IDs that I've been talking about so much. If you've got a bunch of jobs and you know they're all messed up, then you can say scancel-u and your username, and you can cancel all your own. Don't try this in anyone else; it won't work. You can only cancel your own jobs. Um, or you can cancel jobs belonging to you that are in a certain state, etc. There's other options here. This works both on a job that is already running and a job that has not yet started. So if you submit a job and it hasn't yet started and you discover, oh, wait, I didn't mean to do that. I meant to do the other thing. Then you can just cancel the waiting job, the pending job, and submit a new one with SBatch with corrections. You don't lose your place in line in the sense of remembering at the grocery store that you forgot to buy something and leaving the line and coming back. Priority when we start the next job is not a function of when you submitted your job, or rather, it's a very weak function. It is one of the factors that goes in, but it is not the dominant factor. So there is basically no penalty to your priority when your job is going to get scheduled if you cancel and submit a new job. Don't worry about losing your place in line. If the job's already started, obviously it'll have to go back and wait again. But if the job's already waiting, it does not affect very strongly your position in what's going to get run next in the queue. All right, now we come to the question that showed up in the chat about what happens if the job runs over the time limit and hasn't finished. When the time limit is reached, the job will be killed. There may be another half minute or a minute of grace after that. Maybe don't count on that. The reason you've got a job, we've got a time limit there, is basically safety. I think you don't technically you don't have to give a time limit, but the default time limit, we don't publish it, and it's very inconveniently small, and we just encourage you always to give a time limit. You're probably familiar with the thing that you can do with computers, which is to get something going that's actually doing nothing useful, but just sitting there spinning its wheels. This takes a number of forms, but basically this is our defense against that. You should have some idea, is this calculation going to take a minute, an hour, a day, a week? And give it more time than that so that it can get done in case your estimate was off. You don't want it to be 5 minutes from done and gets killed and you lose some results. So give yourself a little bit of extra time, but not enough time that if it stalls and it's doing nothing, then it just sits there doing nothing for a day or a week. Give it enough time that it should be able to get done what it needs to do, and if something goes wrong, it'll eventually be caught and terminated. This is all part of being a good neighbor. I'll remind you again that these high-performance computing clusters that AceNet and the Alliance run have got something in the order of 10,000 users, and on any given day, there will usually be a few hundred sharing the particular cluster you're using. These are a public resource. Use them responsibly and share them properly, and one of the things do is put up guardrails against things going wrong, like your job running too long because something unexpected happened. So, yeah, and we talked about the syntax earlier. Various syntaxes are accepted here. The two that I recommend are either days dash hours colon minutes colon seconds or hours colon minutes colon seconds. If you just have one colon, it's a bit ambiguous. Great. Now, more resources you can request. The first resource that we ask you always to request is time. The second resource that you can request, and frequently will, is CPU cores. The great benefit of high-performance computing clusters, there are so many computers and so many CPU cores there, and so we can run programs in parallel. A parallel program simply means one program running that can use multiple CPUs at the same time. You can also run multiple programs at the same time. I'll come back to that. So if you want to run a program that uses multiple CPUs at the same time, you're running in parallel. And the thing that's important for you to know is there are two broad classes of parallel programs. First is threaded or shared memory programs, or multi-threaded. These are all words for the same thing. So that's first class. And the second class is distributed memory or process parallel programs. And we have, and it's also possible to have hybrids that are both at the same time. But we have two different parameters for requesting CPUs from Slurm. First one, dash CPUs per task, will give you all CPUs on a single host, which is good for the first class, threaded or shared memory. Dash n tasks per node will give you CPUs on multiple nodes, and then you can ask for multiple nodes as well. It can be one node, by the way, if you like, that's fine. And then the total number of CPUs that you're requesting is just the product of those two numbers. Those three numbers, CPUs per task, n task per node, number of nodes. Beg your pardon, there's three there. Let's see, and I'm going to expand upon this a bit. The most common class of parallel program these days is shared memory. They're also called multi-threaded applications or occasionally just threaded applications. If you're looking at the documentation and you see the word threads somewhere in there, then you're probably looking at a shared memory application. If it is obvious from the documentation that it is expected to be run on just one single computer and not a network of computers, then it's almost certainly a threaded or shared memory application. The key feature in any case is the second bullet point here. All cores must be on a single machine, all CPU cores. So how then you tell the application, how the application decides how many cores it's going to use then there's a great wide range of possibilities here. Some programs will simply look at the number of cores that are on the machine they're running on and try to use that many. That's not always a good idea on our Alliance clusters because there may be other people running on the same machine and you should not have all of those cores. We try and help you identify such situations when they come up. Some applications are a little unfriendly that way. Most applications, even if they try to do that by default, have some way to set the number of cores they should use. Some of them get it from an argument. When you invoke the program, there's like an argument -t or --threads or -p or -n or who knows what they call it. You got to read the documentation. And you just supply a number to that argument. In this example, we'll pretend it's called -t. And if your Slurm request then is give me 4 CPUs per task, like shown here, then you want to run the program, some program -t4. Now, little trick about human psychology. If you have in your job script CPUs per task equals 4, and then some program -t4, and then later on you decide, okay, I don't want to run this with 4, I want to run it with 6 or 16, then being a human, you will probably change it in one place and forget to change it in the other. I know I would because I forget things all the time. Programmers have dealt with this problem of consistency between numbers for years. The solution is simple. You define a variable that contains the number 4. You set that variable once and then use the variable everywhere else. Slurm defines that variable for you. So here we have Slurm CPUs per task, and it's got a little $sign in front of it, which if you were in yesterday's session, you will probably recognize as being the way to expand an environment variable. So when you run a Slurm job, when you write a Slurm job script and you put in sbatch CPUs per task equals 4, then that does two things. It tells Slurm to reserve 4 CPUs per task for your job, and it also causes Slurm, when the job is running, to define an environment variable, Slurm CPUs per task, with a value of 4. So some program -t $slurm CPUs per task. That's always going to be four, or no, more to the point, that's always going to match whatever number you set here in the sbatch directive. Clever, eh? Right, some programs some multi-threaded or shared memory programs get the number of cores from an argument on the command line. Some of them stuff that in an input file, a parameter file somewhere. I haven't got that shown on this slide. Some other programs will use an environment variable. There's a large class of these called OpenMP programs, written with a particular parallel programming library called OpenMP. And OpenMP programs usually get the number of cores they want to use from an environment variable called OMP num threads. Your application potentially could use a different environment variable. Read the documentation. But you can do the same trick with OMP num threads. We need OMP num threads to be defined. We want it to be the same as CPUs per task, so we just transfer the value $slurm CPUs per task into the variable OMP num threads, and then we run the program. Second major class of parallel programs, distributed memory applications. On the 2 slides back, I showed this with the example of --n tasks per node equals some number and --nodes equals 1. The vast majority of distributed memory applications use a parallel programming library called MPI, message passing interface, MPI. And so occasionally I've seen some that used MPI and didn't make that obvious from the documentation. They're not explicitly hiding it from you like it says here. They just sort of assume that everyone knows what's going on. As it happens, MPI and Slurm are what we call tightly integrated. MPI and Slurm will communicate automatically. So when you're launching a program that was written with MPI, you do it with srun, and you don't need to supply any arguments. We have srun MPI program, and there's no there's no n tasks here, there's no extra arguments here. srun will transfer that four tasks per node and number of nodes and all the associated information about which nodes and stuff. We'll transfer that to the program automatically. That's what we mean by tightly integrated. You may see in documentation for MPI programs that it says it should be run with MPI run or MPI exec. This is also true. srun basically is a replacement for MPI run or MPI exec in the Slurm context. It does the same things and a little bit more, basically gives us better accounting. So largely, if the documentation says MPI run or MPI exec, you replace it with srun. On very rare occasions, we find things where srun breaks something. I think I've run across maybe 3 in the last 10 years. They're very annoying, but generally you can replace these with that, and away you go. That's how distributed memory applications using MPI work. Slurm. So we've covered shared memory, we've covered distributed memory. Another resource, we've covered shared memory and distributed memory, how you request CPU cores for these things. So we've talked about requesting time. That's the first dimension of resource that you're going to ask for. We've talked about requesting CPUs and the various special cases that are involved in that. The third resource that you will generally need is memory. Memory, like time, has a default amount we will supply. I think at all sites it is 1/4 of a gigabyte per CPU core, but I'm not going to guarantee that. The sites are free to change that if they see fit. Therefore, it is always a good idea to explicitly request memory. There are 2 most common ways to do that. Slurm, by the way, provides a lot of ways to do everything. I'm just giving you the most common and useful ones here. Slurm, the 2 ways to request memory from Slurm usually are either mem per CPU, which is what it says, amount of memory per CPU core, or --mem. And that second one is actually amount of memory per node, per actual computer that's involved in your job. The memory request, like the time limit, is a hard limit. If a job tries to use more memory than it asked for, then it will be killed, generally. Um, uh, and the reason that we ask you to specify memory is something that many of you are probably completely unaccustomed to thinking about. If you've been working on your own laptop or whatever for any length of time, you may be vaguely aware that when you bought it, it had, I don't know, 16 gigabytes of memory or something like that, whatever number. I think mine has 16 gigabytes. And that's probably the last time you thought about memory. And so you come to an HPC cluster and we're suddenly asking you all the time, how much memory does it use? How much memory does it use? It's a little bit annoying. I recognize that. Um, the the reason that we insist you get familiar with memory usage is that um, you may have had this experience of you get like so many tabs open in your browser that everything starts to slow down. What may be happening there on your personal computer is that you've actually exhausted those 16 gigabytes of memory with all the tabs you've got open in your browser. And so the operating system is now trying to use your hard drive or your SSD storage as spare memory. But the hard drive or the SSD is much slower than the RAM, and so everything slows down. The point of a high performance computing cluster is high performance. We don't want things to slow down because the operating system starts using slower storage, disk or SSD, as spare RAM. It does terrible things to performance. It does not turn over jobs quickly. It does not allow people to get the research done in the most efficient fashion. So basically, if a process exhausts physical memory, things either crash or they get too slow. And again, you're living in a shared environment where there are other users who may be running things on the same compute node, possibly as you are. And so we need to know where to put up the walls between jobs so that if your job uses too much memory, theirs doesn't die. And if theirs uses too much memory, yours doesn't die, right? Because if we exhaust all the memory on the machine, everything goes pear-shaped, as they say. Everything stops working. We've got different amounts of memory in different hosts. People will usually ask, so how much memory can I ask for? Well, the most of our machines are actually built. Oops, that didn't go where I wanted it to. Wanted to go here. I'm going to go look at, take you over and look at the Alliance technical documentation. This is just docs.alliancecan.ca. It's got all the technical documentation. You've probably already seen this, but down the side here we have resources, and basically it just starts with a bunch of clusters. So I'm just going to take the first cluster on the list for alphabetically first, and we're going to roll down to node characteristics here on the page on fur, and it's going to have a little table, and it says there are 864 nodes, which have 192 cores each. That's CPU cores. And they have 750 gigabytes, or if you like, 768,000 megabytes of available memory. You may have heard that computer people are weird and they count by 1024s instead of 1000s. That's what's going on here. 750 gigabytes is 768,000 megabytes, sort of. Don't probe that too carefully. But this is about memory. So that's the amount of memory on an individual node. So back at the slide deck then, if you want to know what the maximum amount of memory you can ask for is, you look at that table and see what there is on a node. You may also notice from that table that we have a few large memory nodes. Well, no, those actually GPU nodes. Well, they have a little more memory. Here's the large memory node right there. I can highlight it. Sure I can. We only have 8 of these at fur, but they've got a lot more memory, 6,000 gigabytes. That's 6 terabytes instead of 750. Okay. So that was memory. Next. Oh yeah. All right. Here's the one and only interactive part of this class. I'm sorry there's not more things for you to do here. This is very much a brain dump. I apologize. We haven't figured out how to make this more workshopy. Maybe another year. But this is the one interactive session. No. You in the room who are still awake and paying attention, how many of you are interested in using GPUs? Give me a green sign for that. And if you're like, I don't care about GPUs or I don't know about GPUs, give me a red sign, a red X. So green check. Trying the responses not in the chat. The chat's okay too, but just generally. This is also my secret way of figuring out how many of you are actually paying attention and can find the response keys. Great. I've got 3 not terribly interested, 5 not terribly interested, 2 interested. This is breaking down more or less the way I expected it would. 3 people interested in GPU, 4 people interested in GPUs, 3. And a whole lot of you not responding. All right, that's fine. Slightly under 50% of you, maybe 2/5 of the room are interested in GPUs. Cool. So let's go on and talk about GPUs for a few slides. If if you're not familiar with GPUs, I'll just give you sort of a couple sentences. You've all heard about AI and large language models and generative AI and all this stuff that is changing the world right now. Most of the revolution that has brought AI to the forefront in the last few years is built atop the technological advances in GPUs. GPU stands for graphics processing unit. They began as basically a gamer's device for, painting pixels to the screen real fast while you're playing Doom or Fortnite or whatever you're playing. It turned out that the linear algebra involved in painting graphics to the screen real fast were the same linear algebra basically as needed to train large language models and generative AI things. All these amazing AI innovations in the last few years have largely been built atop the same technology that was used for gamers' GPUs 10 and 15 years ago. So we call them GPUs still, but really they're more properly general purpose GPUs. You can do graphics with them, but largely we don't. The graphics card in your computer you've got now is fine for that. These GPUs we're using for AI, for molecular dynamic simulations, for fluid dynamic simulations, for various other things in high performance computing that involve a lot of linear algebra. And they are in very high demand, as you probably know. But we've got some nodes. Let me flip back and point out that that page on FIR. We have at FIR 160 nodes, each of which has 4 NVIDIA H100s at it. So that's 160 times 4, 400, 640, I think, NVIDIA H100s. That's a lot of GPUs. It's still not nearly as many as our users wish we had. So you get at these things through the job scheduler, through Slurm. The syntax you want, there's several of them again. One of them is -- GPUs equals. I think I'll show you another one in another slide. And usually you might need to do some module loads any job script, you're probably gonna need some module loads. I hope you learned a little bit about that in previous 2 days sessions. To Slurm in this sbatch directive here, we ask that you always specify what model of GPU or fraction of a GPU you need. There are different kinds available at different clusters. The documentation page I just showed you showed that there were H100 models at Cedar. Sorry, put the noise. I said Cedar. FIR. There are 4 H100s in each the GPU nodes at FIR, rather. Let me go back to that page right now, actually, and point out something else. So each one of these nodes carrying GPUs has 48 cores and little over 1,000 gigabytes of RAM and 4 H100s. So if you have a calculation that is going to use one H100 GPU, then we ask you kindly to remember that you're working in a shared environment. And unless you really, really need them and know you need them, please ask for like one H100 and no more than one H100 is a quarter of the GPUs, right? And so please don't ask for more than a quarter of the CPUs, which in this case would be 12. And please ask for no more than a quarter of the memory, which would be around, I guess, about 250, not quite 300 gigabytes of RAM. And by the way, this is in GPU world host memory. The device memory is over here, 80 gigabytes per GPU. If you know the difference between host memory and device memory. And if you don't, if you're like, what are these words Ross is using? Don't worry about it. The main thing I want to point out here is if the page talking about the cluster says there's 4 GPUs per machine, please, unless you really, really need more, don't ask for more than, if you're using one GPU, use a quarter of the memory and a quarter of the cores. Keep things proportional. There may be some cases where you can't keep things proportional. That's fine. If you need our help sorting out what the best thing to do is, please write to support@tech.alliancecan.ca and we'll find what you need to do. Okay, let's see. Back to the slides. So that's what this is about. And there's a documentation page on using GPUs with Slurm that will expand on more of this. The new GPUs, the H100s that I just showed you on the FUR page, and we have H100s also at NIBI and at Rorcal, and we have A100s at Narval, which are not quite as new, but still reasonably up to date, are very powerful. And we saw in 2024 that people would reserve A100s. So this is like the previous generation A100s, not as powerful as the H100s. The A100s, people would reserve one, and on average, they were using maybe 50% of the capacity that they'd asked Slurm to give them. They'd reserve a GPU and maybe it'd run at 50% capacity. In 2025, we replaced a whole bunch of these things. Well, the A100s are still there. We had a bunch of older ones, V100s, P100s. I can't remember what else there was. They've been replaced with H100s, which is way more powerful, but we don't have as many of them. Basically, the H100s is what NVIDIA was selling in 2025, and so that's what we bought, but we couldn't afford as many of them as we originally had V100s and P100s. So we've got more power, but they're in fewer individual GPUs. So there's 2 things that we do to try and make sure that as many researchers can get as much research done as possible without wasting it, like shown here in this 50% figure. The first solution is this. You can ask for a fraction of a GPU. This is called a MIG. MIG stands for multi-instance GPU, but the language gets all kind of confused. Don't try to figure out the etymology too strongly. Basically, in common speech nowadays, a MIG is just a fraction of a GPU. The sort of fractions we're talking about are basically 1/8, 2/8, 3/8, or some sources will say 1/7, 2/7, 3/7. And whether it's 1/7 or an 1/8 is a matter of debate. I've seen a debate about that. It was not illuminating. Anyway, so basically an A100 is worth about 7 A100 1G MIGs. So here's the terminology. We talk about a MIG as a fraction of a GPU. MIGs come in different profiles or flavors, if you like, 1G, 2G, 3G. And each fraction of the GPU computing comes with a fraction of the GPU memory, the device memory, 5 gig, 10 gig, 20 gig. And here's some examples of what that looks like in terms of a Slurm request. I'll actually take you to a page that gives you the complete list of abbreviations for the GPU types in just a moment. Here's some H100 profiles, again, 1G, 2G, 3G fractions, or MIGs. Let me actually find that page right now, because that's what I'm talking about. So what I'm doing here is just going back to the Alliance technical documentation, and my favorite thing is the search box up here in the upper right-hand corner. I'm just going to type in MIG there. It's going to take me to the page on multi-instance GPU. And oh, fiddlesticks. This is not the page that actually gives me what I want, so I need to do a little bit of reading. And that's about NVIDIA. Oh, I know. There really ought to be a link here to a different page. I'm sorry, this should be easier. I'm figuring out as I give this talk an improvement I should make to the documentation. There's another page called Using GPUs with Slurm, which was linked on the earlier slide, that actually has the table I'm looking for. There's all the MIG types, synonyms, and the major things there. So I can tell I'm losing some of the audience who don't care about GPUs. So it's time we move on from this. There is documentation on all these things on the website. Now, let's get back to something a little less theoretical, as someone in the chat just put it. Quick review. You need a job script. You submit it with SBatch. You can check its status with SQ. If you need to cancel it, you can do that with scancel. You start the whole, and then there's requesting the resources, time, CPUs, memory, potentially GPUs if you care about them. The start of the whole thing was log onto the cluster, get your code and data on there. So if you've got some code in R or Python or C or Fortran or Java or whatever, then you transfer your code onto the cluster using one of the tools that we showed you yesterday, the day before, probably the day before, maybe Tuesday. And if it's possible, it's kind of cool if you play with a little bit on your own local laptop, just so you can figure out how it works. That's not always possible, but if it is, it'll probably pay off. And then you get the code and the data onto the cluster, and you try it out with a really small amount of test data, something that maybe should take 5 minutes or less, hopefully. You can do that just on the login node without interacting with the scheduler if you want. We ask that you kindly keep your use of the login nodes down to, no more than about 5 or 10 GPU minutes in a single run of the program, and no more than about 4 gigabytes, hopefully, RAM, but we don't enforce those strongly. Once you've run it suitably on the login node, then you just take the commands that the minimal set of commands that you use, so the job script that you would get out of what we showed you yesterday, and stick some Slurm parameters on it, estimate how much time you think it's liable to take. Still talking test case here. How much time it should take, how many cores you want it to use, how much memory you think it's going to take. Put in a small test job that just asks for a small number of these things. I talked earlier about how the order in which we decide to run things is not strictly a first come, first serve thing. It's mostly depends on how many resources you ask for. If it's only asking for a few minutes and a few cores and a little bit of memory, it'll probably run quite quickly, like right away, most likely. So that's this sort of the launching pad here, is try it out in the login node and then put together a small test job. Excuse me. There's another way you can interact with the scheduler besides just SBatch that is also good for testing. This is called an interactive job. There are 2 ways to run an interactive job. The commands are salloc or salloc. People pronounce it differently, and srun. They take most of the same options as batch. You can ask for time, as shown here in these examples. You can ask for number of tasks, CPUs per task, etc. You can ask for memory, and so on. You can ask for GPUs. If you run salloc, what that will do is that will give you an interactive shell on a compute node. So it's going to look something. I'm going to try. Whoops, I didn't have a login going here. I'm just going to log in and show you what that looks like very quickly. salloc dash dash time equals 0 hours, 5 minutes, 0 seconds, dash dash mem equals 1 gigabyte, dash dash CPUs per task equals 2. Oh yeah, I'm going to need to ask it for an account. I forgot to talk about accounts yet. Most of you will not need to supply an account parameter. I do because I have access to multiple accounts. And it gives me a little static here I don't really care about. And then it takes a few seconds, and then it gives me a prompt on one of the compute nodes. And I can do my calculations here. And if after 5 minutes have gone by, whether I'm still doing things or not, this job will be ended. So I'm just going to leave it there and let it end, which is not an efficient use of resources, but it's only 5 minutes. So for demonstration purposes, I'm going to let it do that. But here you've got Slurm CPUs per task. You've got the environment variables defined. See up here, I put CPUs per task equals 2. Down here, I've got an environment variable with that value. There are other environment variables like Slurm job ID, for example. That number there is the same number it told me here. It was giving me, and so on and so forth. And I can run my code, and I can watch it crash, and I can look at the memory, and I can rerun my code, and I can go back and forth here. If I wanted to be doing something in R, I'd probably have done a module load R, and I'd be running R interactively like this. Don't see it save workspace. If I want to be mess about in Python, I might, module load Python, beg your pardon. I'd probably be doing something like this and working interactively in Python. Or maybe I would be doing Python, my script.
Everyone, I'm missing Sal.
Somebody's got a mic open. Could they close their mic, please? Thank you. I don't actually have such a file sitting around, so that's not going to work. Anyway, I hope you get the idea here. So that's use of salloc. Just get some time on a compute node. You can ask for a way more memory and spend way more time than we like it for you to do on a login node. That's the advantage of salloc. And you also get the complete Slurm environment. So things like environment variables and other stuff like that will be much closer to where your batch job is eventually going to run. The other alternative here, srun, just is basically the same thing, except you can say what application to run, and it just runs it directly rather than giving you an interactive shell prompt. You can ask for arbitrary lengths of time, but at most sites, you will probably have better luck if you ask for 3 hours or less. Ask for 3 hours, and you might not actually get the session. It might just sit there with this queued and waiting for resources prompt for a long time, and you don't actually get anything done. So try and keep your tests down to reasonably short time periods, or your interactive jobs rather, down to short time periods. Someone in the chat asks, for salloc, do you always have to specify an account, or can it pick your account by default? Most of you, it will pick your account by default. If most of you new users will only be associated with one single account, and so you do not need the -A that I gave. I need to do that because I've got access to several accounts. I'll tell you what, I'll demonstrate. I'm a little bit off on a tangent here, but I'm going to demonstrate the same thing and take off the account. And if you see a message like this, then that means you have multiple accounts and you will need to specify one. Conveniently, it shows me a list of what I can use. in the notes here, and it will do the same for you. So if you see this, if you see one of these error messages, just read it. We'll talk more about that in the slides to come too. Okay. Interactive jobs, good way to test how things are going. So the salloc thing or the srun thing worked on a small job. You're pretty confident you know what's going on. Just submit an sbatch. Use sbatch to submit a job script and see if that goes the same. If it's a small short test, again, it should run fairly quickly. You should get feedback quite quickly. And then you can, one of the things you can do, although it may not be all that informative at this stage, is you can see if your runtime CPU and memory requests are reasonable. There's a couple of ways to do this. The old-fashioned way is to use a command called SEF or SEFF. That stands for Slurm efficiency. Again, you need to supply the job ID, and SEFF will pull the Slurm records of the run for that job, and do a little bit of basic arithmetic, read the big messy log files and do a little basic arithmetic and show you whether it thinks your CPU and memory requests are reasonable. It's going to look like this. So there was a job ID 9765432, run SEFF on it, and it tells me, yeah, okay, that was the job ID. I know. It tells me what cluster I'm on. Yeah, I know. Here's the interesting stuff down here. We were asking for 16 cores per node, and it used 5 hours and 11 minutes of CPU time. Yeah, right. 5 hours and 11 minutes CPU time, and there was 7 hours and 22 minutes of core wall time. What's that mean? Hang on. Wall clock time was 27 minutes. Okay. If you multiply 27 minutes and 40 seconds times 16 cores, that will give you, I promise, 7 hours, 22 minutes, and 40 seconds. So that's the maximum CPU time you could possibly have used. It actually booked 5 hours and 11 minutes, and that's 70%, 70.45%. So that's your CPU efficiency. That's not bad. It's certainly using way more than one of those 16 cores. If the efficiency here was down around what's 1/16 of 100, somewhere around 6% or something. Sorry, I can't do the math in my head. If this efficiency was way down low, I think, ooh, maybe it's not actually using the cores you requested for it. This is using most of the cores, not using them full flat out. This is okay. We might be able to do better, but no one's going to get in your face about a 70% CPU efficiency. This is not too bad. Also, memory efficiency. Okay, here's a little worse. You asked for 50 gigabytes, and it only used 3.5 gigabytes at the maximum. So probably if you're going to run more jobs with the same code and roughly the same input, then you could probably reduce your memory request a lot. You might be able to bring it down to like 4 gigabytes instead of 50. Or maybe you want some intermediate number because there's going to be some variation depending on your input. You need to know a little bit about your application. There's a lot of variation here. So that's the old school way to do it. The new fancy way to do this actually is to, whoops, that's not the one I wanted. I wanted this one here. I'm going to go back to one of these cluster pages and point out that at the top of the description of one of these clusters, NIBI in this case, we have something called a portal and a link to portal.nibi.sharknet.ca. I've already logged in at that portal to spare you watching me go through the authentication stuff. And I went to job stats, and I get this page. I'm not actually running anything here right now, so this stuff's all blank, but I can see some of my recent jobs here. Can I find one that's, oh, they're all going to be terrible. These have been terrible interactive jobs using virtually nothing. But I can get a graph that shows my CPU usage, which was rubbish in this case, and my memory usage, which was also rubbish in this case. The job was very short. There's sampling, so I don't really have good figures here. Can I find something a little longer? I didn't have quite have time to queue this up properly before I came to this talk. Is this one going to be a little better? Okay. This job, actually, it's got some warnings up here. You can read those, but I can see down here my CPU efficiency. I asked for 4. I'm not even using 1. Terrible efficiency. I asked for 16 gigabytes of memory, I think is what that says, 15.6 gigabytes of memory. And maximum used was about 1.7. So the portal, we have portals available for most, but not quite all of our sites. You can basically use it to do the same thing as we're showing in this slide with Ceph, only graphical, with graphs that show you usage over time. So you can learn more things from the time sequence as well. I need to find a better example for the next time I do this talk. So now, another thing that I want to try and give you here is some idea of where to start when things go wrong. So let's talk about troubleshooting. There are several classes of things that can go wrong. The first is you type sbatch and it gives you some static and doesn't work. It doesn't give you a job ID back. SBatch, I find, is really actually very good about giving informative reasons. Not 100%. Sometimes it's a little obscure, but mostly it's pretty good. So here's one. SBatch error, batch job submission failed. Requested time limit is invalid. Missing or exceeds some time limit. So that's what I've got. And this example is just I'm asking for, like, I think a month of wall clock time. And at none of our sites will we accept a job that wants to run for a month. I think the maximum we'll currently accept at any site is a week, and some sites may be shorter than that. I'm not sure. Might be 28 days still at one site. Anyway, the point I'm making here is that the message tells you, look at the time limit. Here's another one. Memory specification cannot be satisfied. Requested node configuration is not available. The requested node configuration, that may be a little more obscure, but basically what these two things are saying, memory specification cannot be satisfied and node configuration unavailable, is we don't have any computer nodes that are big enough for the amount of memory that we asked for here. So I've already shown you how to see how to find a list of node configurations, including the maximum amount of memory they're carrying. Check against that. And if you're still confused, which can happen, then write support@tech.alliancescan.ca. Will tell us, show us the job script, tell us what cluster you're on, tell us what you're trying to do. And if there was a job ID, well, you haven't got a job ID in this case, so this wouldn't help. But job script, what you're trying to do, what cluster you're on, and we'll help you troubleshoot these sorts of things. But the sbatch command is pretty good about usually giving you something you can figure out yourself. So the second and far more common situation, or far more time-consuming situation, I should say, is that a job runs, but you didn't get the result you expected. You didn't find the output where you thought it was going to be. First, try and make sure you know all the places where you might get output or error messages. Did you look in the slurm-jobid.out file? Have you found it? Have you read it? Is there an error message near the bottom or near the top that you can start with that gives you a clue? Did your job script redirect output some other file? Have you looked in that file? Are you running an application that sends output to certain files, even when you don't give it a redirect or doesn't send things to standard out? A lot of applications will write things to a bunch of files, like they'll have their own log file or something. Look in there, see what it says, see if you can make anything in the message. If you can't make anything, if you find the messages and can't make anything of them, then write to support@tech.alliancescan.ca and show us the files or tell us where to find them on disk so we can read them ourselves. and we'll help you figure out what these obscure error messages mean and what you can do about it. Um, you can also use Ceph to see whether something went wrong, like maybe running out of memory or something. Here's an example. So just job 1, 2, 3, 4, 5, 6, 7, 8. In the standard output file, slurm-blah.out, there was a message that said Slurm step D error detected 1 kill events in step blah.batch.c group. To most of you, that's probably a lot of gibberish, right? It just sounds kind of like it says error, and kill sounds kind of scary. We use this example because it's actually a fairly common situation. It's not all that scary. OOM means out of memory. So there's a particular Linux subsystem that will deal with programs that are using more memory than they're allowed to. That subsystem is called the killer, out of memory killer, and it kills processes. It's not actually a murder. We're just talking about software here, so it's fine. But yeah, now you know what stands for. It stands for out of memory. So if you see somewhere in the messages, you've now got a hint. Wait a second, maybe I've got a memory problem. And let me show you a couple of Ceph outputs for a couple of jobs. So this job 678, actually in the Ceph output in state, it says out of memory, which is much easier to read than kill. So that tells you right there what's going on. Great. Weirdly, down at the bottom, it shows memory utilized 11 megabytes, which is only 18% of the 60 megabytes asked for. What's going on? If it ran out of memory, shouldn't that be showing 100% or 110% or something like that? No, it should not, because these things in our, well, there's various implementations. Some implementations will sample at some very short but finite time period and will not catch the latest thing. The more likely case is that this was the amount of memory that was used before your program asked for more than it could get. So it tried to go from 18% to something north of 100%. And at that point, the operating system said, nope, out of memory, shutting you down. But anyway, the point here is that there's a nice clear message in the state output from Ceph. Second example, right-hand side of the screen. Job 679. Completed memory utilized 52%. That's actually, there's actually nothing going wrong with this one. If this job died, it was not because it ran out of memory. So you can sort of conclude the negative there, and you should be looking for some other problem. As far as Slurm is concerned, this one was fine. But that can also happen if an application stops itself, like an application might get bad input, for instance. You've got a bad input file, the application will go, nope, I'm done. Slurm says, okay, application's done, it's all good. Slurm is not going to read the output from the application that says bad input file, or probably some more obscure message, because applications are also software written by human beings. Okay, we're getting very near the end. Let me review some high points again. I pointed out somewhere in the midst of this rant that this is a shared resource. These high performance computing clusters have, on any given day, typically hundreds of users and are running thousands of jobs. These are all people like you, researchers, trying to do interesting new things. And these things are all funded by the taxpayer, and who through the machinery of government want to see good research get done. So try to request the resources you need, and not more than that. Give yourself a little bit of room, because computers are a little bit unpredictable. Time in particular is a bit flexible. A job that runs in 1 hour one day might take an hour and 15 minutes another day because the I/O, the input output, is just slower the next day. There's more competition for the storage array or something, or it gets run on a different piece of hardware that's a uh, different age and runs a little slower or something like that. So leave yourself margins of errors. There's nothing quite as annoying as having a job almost be done and then running out of time, and then you got to run the whole thing again because you didn't have checkpoints. We should have that in this slide too, checkpoints actually. If your application has some way to save state and restart from the last save state, and you want to run for a long time, then for gosh sakes, make sure you're using that checkpointing capability to save state every so often, so that if it is terminated, not because it ran out of time, but maybe we had a lightning storm over that facility or some other power event caused it to shut down. All kinds of things can go wrong. Make sure that you can restart with a minimal loss of effort. If you're requesting a lot of resources, besides the consequence that other people can't use those resources at the same time, the third bullet point here, you should probably understand, as I mentioned earlier, the major factor that determines how long it's going to take for your job to get scheduled is how much resource it's asking for. How long is it going to run, multiplied by how many cores, multiplied by how many memory, with possibly an additional factor of GPUs. Basically, the size of that sort of conceptual box of time times CPUs times memory is approximately the thing that determines how long your job's going to wait. It's a lot more complicated than that, and I don't have time to talk about that even in this 90-minute talk. But very loosely, the larger your job, the longer it's probably going to have to wait to get started. There's also a lot of variation from day to day, so unfortunately, it's kind of hard to get good empirical numbers on this. Moreover, due to another aspect of the priority system that I also don't have time to talk about today, the more resources your job, the more jobs you run, and the larger they are, the lower is the priority of the next job that you submit. Basically, each research group has a pool of priority, if you like, and that pool is drained by the number and size of jobs, basically the amount of resources that you're using over time. It's also refilled at a constant rate, but you can drain it a lot faster than it gets filled. And so if you've run a lot of really big jobs recently, you're going to have a hard time scheduling the next job until you wait for a week or so for that pool of priority to refill. Okay, so there's some reasons, some self-interested reasons why you should only request the resources you need, and some publicly minded reasons why you should only request the resources you need. And the caveat, make sure there's a little margin there so you're not having to redo stuff unnecessarily. More best practices. I mentioned early on that when you're running your very first initial test on a login node, try and keep it below 10 CPU minutes and like 4 gigabytes. When you get past that size, if you're still in testing mode, then either use interactive test with salloc or srun, or else jump to small batch jobs with sbatch, and then scale up to there to the full problem you're trying to solve. We showed you some cool tricks you can do with shell loops yesterday in the shell scripting class. Please don't apply those cool tricks to submitting jobs. If you want to do a shell loop inside your job script, sure, there are perfectly good uses for that. But submitting a bunch of jobs with a shell loop, basically what you're doing is you're sort of peppering the scheduler with a lot of like millisecond or microsecond separated requests. The scheduler is tuned to expect human beings to be submitting jobs rather than machines to be submitting jobs, so it's easy to overload it that way. If you have a lot of little things to run, which is an entirely ordinary and acceptable use case, then look into something called job arrays. We didn't have time to get into them here in this 90-minute session, but there's documentation there. Actually, I'll go flip back to the documentation page and bring that to the front. We have down here on the side, we have a whole thing in the left sidebar called running jobs. This is your key documentation about the scheduler running jobs. It's long. It's got pretty much all the stuff I've talked about today and a few things more besides, including array job right here. The idea of an array job is basically you type sbatch once and it'll run a whole bunch of different copies of the job, parameterized by something called the array task ID, which comes as an environment variable. There's a whole separate page on job arrays. Job arrays here. There. So explore the documentation. Running jobs over here is your starting point for all the topics I'm talking about today. Also, try to avoid really, really short jobs. Like under 10 minutes or 15 minutes. Different people have different opinions over what the right line is here. It'll usually take several seconds, maybe in a bad case up to a minute, to get a job scheduled, started, and cleaned up. And that's not counting the waiting time if the system just decides, okay, I can't start this right now, I don't have the resources. Just the business of figuring out whether it can find the resources, getting the job moved to the right node, started, and then cleaning up after it. Consider that to take about a minute when you're calculating these things. If that takes a minute and your jobs are only running for 5 or 10 minutes, then you're talking an overhead of 10 or 20%. You can do better than that. If you've got a bunch of 10-minute tasks, stuff them into a longer job and use a shell loop to like loop over them or something. Or use one of these other tools that can manage these things in a more sophisticated fashion. There's New Parallel, Glossed, and Meta, each of which have their own page on our documentation. Be aware of input-output. One of the most surprising things about running on an HPC cluster is that sometimes, despite the fact they're these big supercomputers, sometimes the input-output is slower than it is on your personal computer. And that's because that storage, the input and output, is going to the storage array, which is shared by all the other hundreds of people using it that day and the thousands of jobs they're running. Consequently, sometimes it's very common for input-output to be the bottleneck. Each of our compute nodes, let me go back to one of these compute pages. FIR is the one I've been showing you. Node characteristics. Each of these compute nodes, besides CPUs and the RAM, and optionally some GPUs, also typically has some onboard storage. We call this node local storage. So each one of these 864 nodes at FIR here, besides 192 cores, also has 7.8 terabytes of, I think that's, honestly, I'm not sure if that's SSD memory or spinning disk. It's probably SSD, but don't quote me on that. Whichever the technology is doesn't matter because this node local storage is right there beside the CPUs and the RAM and does not need to go across the network and compete with hundreds or thousands of other jobs for attention from the storage array software. So if you have a job that needs to do a lot of I/O, it may be your advantage to stage your data to the node local storage, run the job on that, and then stage the output back. There's a page on using this as well. It's called Using Node Local Storage on the wiki. Node local in the search box. Excuse me, using node local storage. There we go. Yeah, there are some limitations on that, which again I don't have time to get into today, but we can advise you on that if IO is your bottleneck. Write support at tech.alliancecan.ca. If you can't figure it out from the documentation, we'll help you out. If node local storage isn't practical, then probably your best move is to use Scratch. And if you don't want to use Scratch because Scratch gets cleaned up or some other reason, then Project is third best, and best not to submit jobs from home at all. At least one of our sites, we traditionally that's actually excluded. If you try running sbatch from a directory in the home file system, it'll block you. Uh, and I think that's about all I've got time for today. A lot of this is here. There's more documentation to read, or you can ask us if you're in trouble. So there's more documentation to read. Um, Besides our documentation, there's also some explicit documentation from the company that makes Slurm. As I said, they're owned by NVIDIA now, but this website is still SkidMD. Let me show you that website just for a moment. Slurm.skidmd.com. The Slurm workload manager here. There's totally release notes documentation, um, including man pages for all the commands. So if you want to know what all the options for sbatch are, you can go to the man pages and you can go to sbatch and read about it here in copious detail. As on any other cluster, you can always do man sbatch and get pages that way. Whoops. So come back to there. Right. And I'm done. And look at the chat now. I think we can probably terminate the recording and we'll